Welcome to the mysteries of the cosmos. The question of whether time can end takes us to the limits of our cosmological knowledge and confronts us with dizzying concepts. To understand whether time can have an end, we must first understand its nature and how it is intertwined with the fate of the universe itself. The concept of end of time can be interpreted in several ways, each with profound implications for our understanding of the cosmos. One possibility is that time ends with the end of the universe, which leads us to consider possible scenarios of cosmic fate. The Big Crunch model proposes that the universe could eventually stop expanding and collapse in on itself, possibly ending time. In this scenario, spacetime would contract to a singular point, similar to the Big Bang but in reverse, potentially marking the end of time. Another scenario, the Big Freeze or heat death of the universe, suggests a future where the universe expands eternally, gradually cooling. In this case, time could continue indefinitely, but in a universe that is increasingly cold, dark, and lacking in complex structures. The Big Rip hypothesis proposes a more dramatic ending, where the accelerated expansion of the universe eventually tears all matter apart. This extreme scenario could lead to the dissolution of spacetime itself, potentially marking a definitive end to the concept of time. Some cosmological models suggest the possibility of a cosmic rebound, where the universe oscillates between expansions and contractions. In this case, time might not have a definitive end, but rather go through cycles of cosmic rebirth, challenging our linear notion of time. String theory and brain models propose the existence of multiple universes, further complicating the question of the end of time. In a multiverse, the end of time in our universe might not mean the end of time in an absolute sense, but only in our local context. Quantum mechanics adds another layer of complexity, suggesting that time might behave fundamentally differently at subatomic scales. Some physicists theorize that at the quantum level, time might not be continuous but discrete, composed of indivisible units called time quanta. The idea that time might be an emergent, rather than fundamental, property of the universe has gained attention in some theories of quantum gravity. If time is emergent, its end might not make sense at a fundamental level, but rather be an aspect of our macroscopic experience. The concept of eternity in modern physics does not necessarily imply infinite time, but rather the absence of time under certain extreme conditions. For example, inside a black hole, the equations of general relativity suggest that time might cease to have meaning as we understand it. The notion of imaginary time, proposed by Stephen Hawking, offers a way around the Big Bang singularity and the concept of a beginning of time. In this model, time behaves like a spatial dimension near the Big Bang, eliminating the need for a defined beginning or end of time. Thermodynamics and entropy play a crucial role in our understanding of the future of time and the universe. The inevitable increase in entropy suggests an arrow of time pointing toward a state of maximum disorder, but not necessarily to a defined end. Some physicists speculate about the possibility of islands of time, regions of the universe where time might behave differently. These hypothetical regions could experience time in different ways, or even exist outside of our conventional time flow. Quantum cosmology explores scenarios where the universe could exist in a superposition of states, including different times simultaneously. This perspective challenges our classical notion of a single, universal time, suggesting a much more complex and multifaceted reality. The idea of a cyclical time has resurfaced in some modern theories, proposing that the universe could go through infinite cycles of existence. In this scenario, time would have no end, but would repeat itself eternally, although each cycle might be fundamentally different from the previous one. The concept of eternal time in some interpretations of quantum mechanics suggests that all possible moments could exist simultaneously. This vision of the quantum block universe challenges our linear perception of time, suggesting that the end might be merely an illusion of our consciousness. The possibility of additional time dimensions, proposed in some string theories, adds another layer of complexity to the question of the end of time. Multiple temporal dimensions could allow for more complex temporal structures than our linear concept of past, present, and future. The role of consciousness in the perception of time raises philosophical questions about whether the end of time has meaning without an observer. Some argue that time, as we experience it, might be a construct of our mind, and its end might not make sense outside of consciousness. The holographic universe theory suggests that our three-dimensional universe could be a projection of information stored on a two-dimensional surface. In this model, time could be an emergent property of this information, questioning the fundamental nature of time and its possible ending. Advances in particle physics and the search for a theory of everything could provide new insights into the ultimate nature of time. Experiments at large colliders and precise astronomical observations continue to provide data that could solve the mystery of the fate of time. The possibility that the universe is infinite in extent raises questions about whether time might also be infinite in duration. A spatially infinite universe could imply the existence of identical copies of ourselves, repeating history infinitely in space and time. The idea of a false vacuum in cosmology suggests that our universe may be in a metastable state, susceptible to a cosmic phase transition. Such a transition could fundamentally alter the laws of physics and the nature of time, possibly leading to its end as we understand it. The concept of quantum information and its conservation could have profound implications for the ultimate fate of time and information in the universe. Some physicists propose that information is never truly lost, which could mean that the end of time does not imply the total loss of cosmic history. The search for a unified theory of quantum gravity remains crucial to truly understanding the fate of time and the universe. Such a theory could reveal whether time is truly fundamental or emergent, and whether it has a definitive end or continues eternally in some form. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video.